In part 9, I started the discussion on fusion. I talked about some of the crucibles used as well as some of the flux material employed. In this presentation, I would like to elaborate a little bit more on the use of flux and also on the crucibles that are sometimes used in the effort of totally dissolving samples. I am Rob Boyko, Boyko Mineral Exploration, and welcome back. Sodium carbonate is undoubtedly one of the most commonly used fluxes. It is not only used for decomposing silicate materials such as clay, rocks, minerals, slags, glasses, and more. It is also used for the decomposition of refractory oxides of magnesium, aluminum, beryllium, zirconium, quartz, and others, not to mention the insoluble phosphates and sulfates. This flux is preferred due to its low melting point of 854 degrees centigrade. When used as a fusion flux, it will convert insoluble silicates into soluble fusion cakes, which become soluble in hydrochloric acid. For example, aluminum metasilicate is converted into sodium aluminum oxide, along with sodium silicon trioxide, both of which are soluble. 1 gram of sample is usually mixed with 4 to 6 grams of sodium carbonate, which is dependent on sample type. It is then fused at temperatures between 900 and 1000 degrees centigrade for 10 to 30 minutes. A nitrate, such as potassium nitrate, may be added at times to prevent the reduction of metals, and if a platinum crucible is used, it will reduce or inhibit the alloying with the platinum. However, some of the platinum from the crucible will be decomposed into the melt. Potassium carbonate is preferred over sodium carbonate for the analysis of niobium and tantalum analysis. This is due as the resulting potassium salts are soluble, as some sodium salts are insoluble. In part 9 of this series, I discussed the dangers of sodium peroxide due to its hygroscopic nature and its oxidizing power. Never use paper when weighing this reagent on a balance scale. In the event that the paper is even slightly damp, an explosion or fire may result. Always use a small porcelain weighing boat or crucible for these types of reagents. Now this reagent is used to decompose refractory materials such as chromite, magnetite, ilmenite, rutile, cassiterite, silicon carbide, and more. Fusion temperatures will range from 500 degrees centigrade to 1200 degrees centigrade, depending on sample material. Below 500 degrees centigrade, sintering takes place. Crucibles commonly used are platinum, zirconium, silver, iron, and gold. Nickel can be used. However, iron crucibles are preferred as ferric oxides are more readily solubilized than nickel oxide. The others are much more expensive. Iron crucibles must be cooled prior to the removal of the fusion cakes. Hot magnetic iron oxide may flake off the crucible. After fusion, chromium cakes are usually removed by soaking in distilled water, then decomposed by the use of sulfuric acid. Now this may leave a yellow stain on the crucible. This can be avoided by adding a few mils of hydrogen peroxide along with sulfuric acid. This yellow staining is the result of the sodium peroxide fusing with the chromite. The chromite is reduced to chromium during the fusion, which leaves the yellow stain. Excess peroxide, when added to the acid, is removed by boiling the solution. Now, rare earth metals, such as those listed in the periodic table having atomic numbers from 57 to 70, are made soluble by sintering, then leaching with distilled water. Digestion is accomplished with nitric acid. This would be the range starting from lanthanum to ytterbium. Potassium bisulfate is actually an acid salt. created when potassium metal is dissolved by sulfuric acid and evaporated to dryness. This reagent has a melting temperature of 197 degrees centigrade. The crucibles commonly used for this fusion are quartz, glass, or platinum. Now, most metals can be dissolved using a potassium bisulfate fusion. However, there are exceptions, such as silicates and sulfates of barium, calcium, strontium, and more. Fusion is normally carried out by utilizing a Bunsen burner. This method avoids cracking any porcelain or glass crucible employed in the process. The lowering of the fusion temperature of the sample is obtained by using potassium bisulfate. As shown, potassium bisulfate starts to melt at 197 degrees centigrade. At 210 degrees, potassium pyrosulfate starts to evolve as a product of fusion, and the water is expelled as water vapor. At 325 degrees, the products of fusion are potassium sulfate and sulfite. The result is that the fusion temperature of the sample may be considerably lowered. Sodium and potassium hydroxides have similar characteristics. Both are highly reactive and alkaline. Potassium hydroxide is more reactive than sodium hydroxide. Now, flux to sample ratios will range from 10 to 1 through to 20 to 1, all depending on the matrix of the sample. Being hydroxides, during fusion, large amounts of water may be the result and will be expelled during the fusion. The result may be excessive sputtering or foaming. This not only results in loss of analyte during fusion, but also presents a safety hazard. Therefore, when using this reagent as a flux, it is slowly melted prior to the addition of the sample material. In this way, the water is driven off from the melt, thus avoiding loss and minimizing safety concerns. Borate fusions are common for whole rock analysis by alkaline fusion. Commonly used in classical chemical assay as a method to solubilize samples for instrumental analysis. However, it is also used for volumetric and gravimetric analysis, both of which will be discussed later in the series. Most commonly used reagents are lithium tetra and metaborate, as was discussed in part 9 of this series. Instrumental is just mentioned, and will not go into detail as it is beyond the scope of this series, and is not usually conducted by a small-scale miner, prospector, or hobbyist. Now, large flux to sample ratios tend to lower detection ratios for instrumental and thus are inferior to straight acid dissolvement. Instrumental analysis for low concentration analytes is conducted in an assay laboratory. However, it is possible to detect lower concentrations of elements using volumetric analysis. Sand, slags, iron, rare earth element ores, zirconium dioxide, niobium, and tantalum can be dissolved using a borate fusion. Any organic compound associated with a sample must be ashed first, and samples containing reduced metals must be oxidized. Crucibles that are used are always platinum. Other crucibles are attacked by the melt. As the melts are quite viscous, the melts must be continuously stirred for homogenization. It is for this reason fusion is not done by a muffle furnace, instead by a Bunsen burner or torch. In addition to, some platinum analyte may be lost in the melt, due to the fact that the platinum group metals cannot be fused with borate. These will remain insoluble and will alloy with the crucibles that are alloyed with 5% gold. Mercury, tin, and antimony will be driven off at temperatures between 1000 and 1100 degrees centigrade, while other compounds that form, like copper halides, are volatilized. Any resulting fusion cake can be dissolved by diluted nitric acid. The solutions can then be divided into aliquots of known values. That is to say that they can be divided into separate samples of known volumes. Last of all, Borate fusions are the simplest, the fastest, as well as the most consistent approach to sample preparation. Sodium tetraborate is best known as borax. It comes in two varieties: hydrous, meaning that the compound contains water molecules, and anhydrous, which means it does not contain water molecules. The hydrous version should be dehydrated prior to use to avoid foaming and/or sputtering. Anhydrous is more expensive than hydrous. One can just purchase a box of 20 multein borax off the shelf at your grocery store and dehydrate the compound. The box will have a label stating that it is 100% borax. All one has to do is heat the compound at 600 degrees centigrade until all water vapor is evaporated, then cooled in a desiccator. Anhydrous tetraborate melts at 742 degrees centigrade. Weighing the compound before heating and after heating repeatedly until there is no further weight loss will ensure that all the water has been driven off. Now, once driven off, melt the borax, then cool it. The resulting glass can then be pulverized or ground down to a powder, resulting in a borax glass. This reagent will dissolve a number of compounds. When cooled, it forms a fairly clear glass. Now, metal elements which may be dissolved in the melt, especially those oxides, will result in different characteristic colors. The coloring of these glassy slags may be used in some instances to identify the metallic element. Boric acid is mostly used for the dissolvement of inert material. This would include, but not limited to, sand, orthoclase, which is an aluminum tectosilicate, titanite, and corundum, which is mainly aluminum oxide. The sample to flux ratio will range from 1 to 4 to 1 to 8. This is totally dependent on the sample matrix or ore type. The flux sample is slowly heated by slowly increasing the temperature to drive off any water molecules, after which the temperature is increased until the sample is fully solubilized as a melt. This process takes about 20 to 30 minutes to complete. The fusion cakes, when cooled, can be dissolved using diluted acids. The remaining boron is removed by adding methanol to the solution, then volatilizing with methyl ester, such as B100. Now, B100 is 100% biodiesel fuel made from plant oils. There are advantages in regards to performing these fusions in conjunction with acid dissolvement of refractory and difficult to dissolve materials. Now, the first is that this method is suitable for whole rock analysis. Now, most minerals, including chromite and zinc, can be decomposed into a solubilized sample. The alkaline boric fluxes act as buffers for instrumental analysis and techniques, but may also apply to volumetric methods. Importantly, it does not require the use of dangerous acids such as hydrofluoric acid for multi-acid digestion of the fusion cakes. And lastly, it is rather a quick process when there are only a few samples to be processed. But like everything else, there are disadvantages, especially when it relates to instrumental, which is beyond the scope of this series. However, these disadvantages also relate to gravimetric and volumetric analysis, which will be discussed in a future presentation within this series. Coagulation and flocculation. Simply put, are a form of minute solids within a solution. In regards to molten solutions, these are small pieces of material that have not melted and remain as solids. This not only degrades detection limits, as these melts will require further aggressive dissolution, and may also result in analyte loss. The detection limits can be 5 to 10 times higher, which is a result of the higher sample to solution ratios compared to straight acid dissolution. This higher ratio makes trace element analysis difficult without analyte separation techniques. Now, ACS grade acids are readily available and are cheaper in cost compared to fluxes. ACS grade fluxes are hard to obtain. This increases the cost of these pure flux reagents, as most of these are difficult to purchase. Some fluxes may also cause contamination. Then there are contaminants from crucibles, dust, ash, furnace chips, which is related to the aging of the furnace, and furnace door linings. Lastly, some flux elements such as lithium, sodium potassium, potassium carbonate, and potassium sulfate cannot be measured. I would like to start summarizing this presentation, along with Part 9 together. I encourage one to stop the video at times to take notes. Sodium pyrosulfate has a melting temperature of 403 degrees centigrade. Potassium pyrosulfate melts at 419 degrees, both of which will fuse the samples at a temperature of up to red heat, or 700 degrees centigrade. The usual crucibles used are platinum, quartz, and most common, porcelain, for the decomposition of oxides of the rare earth metals, including aluminum, beryllium, tantalum, titanium, zirconium, plutonium, and more. Sodium hydroxide has a melting point of 321 degrees centigrade, while potassium hydroxide melts at 404 degrees. Both of these fluxes will fuse between 450 and 600 degrees centigrade, depending on sample matrix. Crucible used for these fluxes are nickel, silver, and glassy carbon. Samples decomposed with these fluxes are silicates, oxides, phosphates, and fluorides. Sodium carbonate melts at 853 degrees centigrade, potassium carbonate at 903 degrees, both of which will fuse between 900 and 1000 degrees. Nickel crucibles are most commonly used, but platinum with lids may be utilized as long as the fusion time is kept short. The samples are typically silicates, such as found on clays and rocks. Others are minerals and glasses. Others are refractory oxides, quartz, insoluble phosphates, and sulfates. Sodium peroxide melts at 460 degrees and fuses at 600 degrees centigrade. Nickel crucibles are most common. However, silver is also used. Platinum crucibles can be used if the temperature is kept lower than 500 degrees centigrade, usually for sintering. Sodium peroxide is used for samples that contain sulfides, chromium, tin, and zinc minerals, as well as acidic insoluble alloys of iron, nickel, chromium, molybdenum, tungsten, and lithium. It also includes the platinum group alloys. Boric acid melts at 170 degrees centigrade and fuses at 250 degrees centigrade. Platinum crucibles are used to decompose sand, aluminum silicates, titanite, and natural aluminum oxide, such as corundum. Borax melts at 878 degrees and fuses between 1000 and 1200 degrees centigrade. Platinum crucibles are preferred for decomposing aluminum trioxides, zirconium dioxide, and zirconium ores. This flux is also used to decompose rare earth metals, titanium, niobium, and tantalum, as well as other aluminum materials, iron ores, and slags. Lithium tetraborate melts at 920 degrees centigrade, while lithium metaborate melts at 840 degrees C. Both will fuse between 1000 and 1100 degrees centigrade. The most common is a graphite crucible, Platinum is also used. Tetraborate salts are used for basic oxides and resistive silicates, whereas metaborates are used for the acidic oxides, such as silica, titanium oxide, and most minerals. Both of these fluxes are not suitable for metal and sulfides. Ammonium bifluoride will melt at 125 degrees C, sodium fluoride at 992 degrees, potassium fluoride at 850 degrees, and potassium bifluoride melts at 239 degrees C, all of which will fuse at 900 degrees centigrade. Platinum crucibles are used for these fluxes to decompose oxides of niobium, tantalum, titanium, and zirconium. The fluxes are also used to remove silicon and for the destruction of silicates and rare earth metals. As was discussed throughout this presentation, the wet-dry method of dissolvement is carried out to decompose hard-to-dissolve and refractory materials. We use fluxes, acids, and crucibles to accomplish this task. There are special methods as well, which I will cover in part 11 of this series. But for now, let's focus on a summary of the applications that are recommended in regards to some of these crucibles that are utilized. Now, borosilicate glass, commonly referred to as just glass, is a general application type crucible. It is transparent and it is fragile. It does have good thermal properties. The downside is that it will be attacked by hydrofluoric and phosphoric acids, as well as alkaline solutions. Now, fused quartz has similar properties as glass. These are also transparent as well as fragile. Used for high temperature applications, these thermal properties are excellent up to 1000 degrees centigrade, after which they start to soften. Now, these too are attacked by hydrofluoric and phosphoric acids, as well as alkaline solutions. Now, porcelain is another high temperature applicable crucible. They are reliable up to 1100 degrees centigrade and are less expensive than quartz. These two, being a type of glass, will also be attacked by hydrofluoric acid and phosphoric acid, as well as alkaline solutions. Platinum crucibles are used not only for high temperature applications, but are also used for corrosive applications. Now, by virtue, these crucibles are not affected by acids, including hydrofluoric acid. However, they can be dissolved in aqua regia, as well as chlorine and bromine waters. They are only adequately resistive to phosphoric acid. Now, during fusion, they may alloy with mercury, lead, tin, gold, copper, silicon, zinc, cadmium, arsenic, bismuth, and iron under reducing conditions. They are also permeable to hydrogen gas at 700 degrees centigrade, or that is red heat. The gas serves as a reducing agent. In addition to, during fusion, reaction with sulfur, selenium, tellurium, phosphorus, arsenic, antimony, and boron, as well as carbon, may damage the crucible. These crucibles are not used for sodium carbonate fusions. Platinum crucibles can be easily damaged as they are soft physically and thus easily deformed, and therefore must be handled with care. The manufacturer usually alloys these crucibles with iridium, gold, or ruthenium in order to give them some structural strength. Last of all, they are very expensive and should be recycled for precious metal recovery at end of life. Now, nickel crucibles are the preferred choice for molten metal hydroxides and sodium peroxide fusions. These crucibles are also suitable for strong alkaline solutions. Zirconium crucibles are generally used for peroxide fusions. They are less expensive compared to platinum and therefore become a good alternative to platinum crucibles. They are very resistive to hydrochloric acid, and they will resist 50% sulfuric and 60% phosphoric acids up to 100 degrees centigrade when heated. Now these crucibles will also resist molten sodium hydroxide melts, but they will be attacked by nitrate and bisulfate melts. These crucibles are actually made of zircaloy, which is an alloy comprising of 98% zircon, 1.5% tin, and traces of iron, chromium, and nickel. Crucibles made of alumina are used for low temperature acidic and alkali melts. They do resist acids and alkali melts, but will be rapidly attacked by bisulfate melts. These crucibles are brittle and must be handled with care. They also require the use of thick-walled containers. Now Teflon will be discussed further in part 11 of this series. However, I am going to mention it now. Teflon is known as PTFE, which stands for polytetrafluoroethylene. This type of crucible is used for special application methods pertaining to corrosive applications. Now, these crucibles are inert to most inorganic as well as organic compounds, except for fluorine gas. Its porosity to the gas is less than polyethylene. These crucibles are only safe up to 250 degrees centigrade, and they will decompose at 300 degrees. The crucibles have low thermal conductivity. Not to mention, they're very expensive. Now, I mentioned polyethylene, and therefore just to include it in the discussion for safety considerations. These are not crucibles, but storage containers that are sometimes used for sample and reagent storage. Now, they are made of a type of plastic that will resist most acids. However, caution must be taken. You see, 16 molar nitric acid and glacial acetic acid will eat right through these containers. They will begin to soften at 60 degrees centigrade, so they must be kept away from heat. They also become porous to bromine gas, liquid ammonia, hydrogen sulfide gas, water, and diluted nitric acid below 16 molar. Well, this concludes part 10 of this series, titled Classical Chemical Assay for Small-Scale Miners, Prospectors, and Hobbyists. In this presentation, I talked about the crucibles used, along with some of their applications. In part 11, I will be discussing briefly some of the special treatments used for those hard to decompose and refractory type samples. Now, I tried to present the information in a way that anyone without a chemistry background would understand, and I hope that I succeeded. Now, if you found the information helpful in this presentation, or even somewhat interesting, or know of someone who could benefit from this presentation, please give it a thumbs up and a share. It's my only reward. Now, I hope this presentation will entice you to view part 11 when it is published. I am Rob Boyko, Boyko Mineral Exploration, and I thank you for watching.